Welcome back to this series on topology. In today's video, we'll be looking at disjoint union spaces. You can find a playlist with all the videos in this series by clicking on the info thing that should appear right now. Suppose we're given two sets, X and Y, which I'll draw in orange and blue. Then we can think of these sets as lying disjointly next to one another. So what we're doing is we're thinking of this entire set here, which I'm surrounding in gray, and this will be the intuition behind what the disjoint union of the set X and Y is supposed to be. Now, if X and Y don't have any elements in common, so they're already disjoint as sets, then the disjoint union will just be the usual union of sets. On the other hand, if these two sets do have some elements in common, we'd like to separate them in this disjoint form of union. So in the extreme case, where we're considering two copies of the same set, A for example, we'd like to think of the disjoint union between A and itself as being two copies of A sitting next to one another. And so in this case, we would want each of the elements of A to appear twice in the disjoint union, while of course in the union, A unioned with itself is just A again, so there every element would only appear once. The easiest way to realize this is just to replace each of the sets in question by an isomorphic copy of the set, such that these isomorphic copies are themselves disjoint. A natural way to do this is just to index each one of the sets and add the index to each element of the set in question. For example, if we have some element small a of the set A, then we would replace each of these copies of A with the isomorphic copy, which I'll call A1, which includes all the elements just as in A. However, now we also add a index 1 to each element in order to distinguish them from the other copy of A, which we'll replace by the isomorphic copy A2. And here, this will have elements of the form A, 2. In this way, we've just labeled each of the elements of the sets in question by the index of the copy of the set that it belongs to. Another way to think about this is that A1 is just equal to the Cartesian product of A with the singleton set containing the index 1, and A2 is equal to a Cartesian product, the singleton set containing the index 2. So in this way, we've managed to distinguish the elements of the different copies of the set A, and now if we were to union A1 and A2, the elements corresponding to the original element small a will now be distinct, because A, 1 is distinct from A, 2. Therefore, in our example, we would define the disjoint union between the set A and itself simply as the usual set union between A1 and A2, or another way of writing this is the set of tuples small a, I, where A lies in AI. Of course, we want to define the disjoint union not just between a set and itself, but more generally for an arbitrary family of sets. So we let X alpha, where alpha lies in some index set A, be an indexed family of sets. Then we can define the disjoint union over all these X alpha, where alpha lies in the index set A, as follows. This is just the set of tuples X, alpha, where X lies in X alpha. Notice that this is exactly the same idea we looked at before, except that instead of two copies, we're considering a family that's indexed by some set capital A. Next, let's look at some features of the disjoint union. Perhaps the most important feature is that each of the X alphas embeds into the disjoint union. This means that we have a map, which I'll call iota alpha, which goes from X alpha to the disjoint union over all the X alphas, where alpha lies in the index set A. How is this map defined? Well, we just map each element small x to the corresponding element in the disjoint union, so we have to map it to the tuple x, alpha. So if we identify the set X alpha with the isomorphic set X alpha Cartesian product with the singleton containing the index alpha, then this allows us to view X alpha as sitting inside this disjoint union, because the disjoint union is just a union over all of the sets of this form, X alpha times the singleton alpha. In other words, for each index alpha, the disjoint union contains an isomorphic copy of the corresponding X alpha. And of course, this is exactly what we wanted in our construction. We want to think of the disjoint union as being copies of the X alpha sitting disjointly next to one another. These inclusion maps, J alpha, are extremely important because they characterize the disjoint union via a universal property. This goes as follows. Suppose that we have, for each X alpha, a map going from X alpha to some set Y. And I'll call this map F alpha. So we're assuming that for each X alpha, there's such a function, F alpha, going from X alpha to Y. Now the universal property for the disjoint union says that in this case, there is a unique map going out of the disjoint union to Y. I'll call this unique map U, making all of these triangles commute. So for each X alpha, we have such an inclusion map J alpha and a map F alpha, and U is a map that makes all of these triangles commute. How is this map U defined? Well, if we have some arbitrary element X beta in the disjoint union, then this is mapped by U to F beta of X. Essentially what's happening here is we're distinguishing cases. Remember that the second index in the disjoint union tells us in what set this element originally was. So having a second index beta here means that the element X originates from X sub beta. And well, if we have such an element X in X sub beta, then the natural thing to do is just to map it to Y using F beta. Now, because this element X comma beta is just J beta of X, this means that applying U to the element J beta of X is equal to, by definition, F beta of X. And this is precisely the condition saying that this triangle here commutes. So far, we've shown that if we have, for each index alpha, such maps F alpha going from X alpha to Y, then we can construct a function U going from the disjoint union to Y that makes all of these triangles commute. The additional claim in the universal property is that this map is unique. The reason for this is that every element of the disjoint union has the form J beta of X for some element X in some X beta. In other words, each element of the disjoint union originates from some X alpha in the family X alpha alpha in A. Now, suppose we had some U prime that goes from the disjoint union to Y and also makes all these triangles commute. Well, then U prime would also have to satisfy this condition down here we had for U, but now because each element of the disjoint union has this form, J beta of X, for some index beta and some element X in X beta, it means that this U prime is completely determined by the corresponding maps F beta here on the right. Therefore, if we want all of these triangles to commute, we have no choice in how we define U. We have to use this definition I gave here. All right. So far, we've just been discussing sets and functions, and we've recapped the universal property of the disjoint union in the category of sets. We would now like to lift this construction to the category of topological spaces. So we suppose that these indexed sets X alpha aren't just sets, but that they also have topologies on them. And now we would like to find some topology on the disjoint union of these X alphas, such that the universal property for the disjoint union also holds in the category of topological spaces. Explicitly, this means that we will want these J alphas to be continuous maps, such that for any family of continuous maps F alpha, to some arbitrary topological space Y, we want there to exist a unique continuous map U going from the disjoint union space over these spaces X alpha into the space Y, in such a way that all of these triangles commute. So the first thing we need to think about is how to make these inclusion maps iota alpha continuous. For this, we suppose that we have some open set U that is a subset of this disjoint union between the sets X alpha. In order for the map iota alpha to be continuous, we need the preimage of U under iota alpha to be an open set in the corresponding space X alpha. So we want that the preimage under iota alpha of U, this should be open. But this preimage is just the set of points X in X alpha, such that iota alpha of X lies in U. But we know that iota alpha of X is just a tuple X comma alpha, so we can replace that here. Another way to think about this set is simply as X alpha times the singleton containing the index alpha, and this whole thing intersected with the subset U. So here we've identified X alpha with its isomorphic copy, X alpha times the singleton alpha. And making this identification one more time, we can just write this whole thing as X alpha intersected U. So what do we learn? Well, if we want these maps iota alpha to be continuous, then for any open set in this disjoint union space, we'll want its intersection with every X alpha to be an open set. All right, so we started with the question of what topology we should put on this disjoint union space in order to make these maps continuous. And we got this condition that we want the intersections of any open set in this topology with each X alpha to be an open set in X alpha. Hence, this condition will limit the size of the topology that we can put on the disjoint union space. In other words, if we would include too many open sets in the disjoint union space, then it might happen that one of their preimages under one of the iota alpha might not be open in some space X alpha. So the question becomes which of the eligible topologies that fulfill this requirement we should put on this disjoint union space. And in order to figure this out, we replace this set Y here again by a topological space that has as an underlying set the disjoint union over the X alphas, and we replace these F alpha by the inclusion maps iota alpha. Now suppose we have a topology tau on this pink disjoint union space and a topology tau prime on the purple disjoint union space. So these can be different in general, but we're going to assume that they both satisfy this requirement and therefore make these maps iota alpha continuous. Now, if this space here on the left is to fulfill the universal property for the disjoint union, then there needs to exist a unique map which is continuous going from it to this purple space. And moreover, this map should make these triangles commute. Now, from the commuting requirement, it's pretty clear to see that the identity on the disjoint union space satisfies that requirement. And so the question becomes whether this identity map here is continuous or not. Therefore, in order for this space here to fulfill the universal property, the identity map from this space with the topology tau to the purple space with the topology tau prime needs to be continuous. What does continuity of the identity map mean? Well, it means that for each open set in tau prime, the preimage under the identity map needs to lie in tau. But the preimage under the identity map of any subset is just that same subset. Therefore, having the identity map here be continuous means that tau prime is actually contained in tau. Therefore, if we want the topology we put on this space to fulfill the universal property, then we need this topology to be the largest topology we can put on the disjoint union of the x alphas that still satisfies this requirement down here. And in fact, one can show that if one endows this disjoint union with the largest topology that satisfies this requirement, then it will satisfy the universal property for the disjoint union. Okay, I moved through this whole argument pretty quickly because it's dual to the derivation we already saw for product spaces. So if this was too fast, then you should maybe go back to the last video on product spaces and watch the argument there and see how it's basically dual to this argument in the sense that we just reverse all the arrows that are involved. We are now ready to state the definition for the disjoint union topology. For this, suppose that x alpha, where alpha lies in some index set capital A, is a family of topological spaces. Then we denote their disjoint union by this square cup symbol that we've already seen. We now put a topology on this space as follows. Given a subset U of the disjoint union, we declare it to be open if and only if its intersection with each of the spaces x alpha is open in the corresponding space x alpha. And just as a reminder, here we again identify x alpha with the isomorphic copy of x alpha, which is a subset of the disjoint union. We saw in the derivation that we want the disjoint union topology to be the largest topology on the disjoint union that satisfies this requirement, and this definition makes this happen because we're declaring every subset that satisfies this requirement to be open. So this means that it's going to be the largest collection of subsets that satisfies this requirement. The only question that remains is whether declaring such subsets to be open actually makes the resulting collection a topology. And luckily this is the case, as you can check. Essentially the reason this works is because each of the x alphas is a topological space, and also we have a compatibility between intersections and unions. Since our discussion has been very abstract so far, you might still not quite see what this definition is saying, so let's draw a picture. What we're given is some family of spaces x alpha, and for simplicity, let's just draw 3 of them. So we have x1, x2, and x3. And now in the disjoint union, we're thinking of these spaces as just sitting next to one another and not interacting in any way. Okay, so this picture describes the disjoint union of x1, x2, and x3. And now the question is, what are the open sets of the disjoint union space? Well, some subset of this disjoint union is going to consist of a disjoint union of subsets of each of the spaces. So all of what I've drawn in orange is some set U. And actually the set U can be written as U1 disjoint union U2 disjoint union U3, where U1 is the intersection of U with x1, U2 is the intersection of U with x2, and U3 is the intersection of U with x3. And now what we're saying in this definition is that a subset U is open if and only if each of these intersections here is open in the corresponding space. Now, of course, there could be an empty intersection with one of the corresponding spaces, but this is okay because the empty set is always an open set. All right, so that's how this works schematically. For a concrete example, let's just consider 2 disjoint copies of the real line. So this is the disjoint union space of R with R. And now if we have some subset of this disjoint union, this is open if the intersection of that subset with each of the copies of the real line is open. Therefore, the open sets of this real line disjoint union with itself are precisely disjoint unions of open intervals. So they might look like this. However, as soon as we would have some set that's not open as an intersection of the set with one of the copies of the real line, then the entire set would not be open in the disjoint union space. For example, if we just had also this isolated point here included in the set, then this set would not be an open set considered as a subset of this copy of the real line, and therefore the entire set would not be open in the disjoint union topology. Next, we'll consider a slight reformulation of the universal property that we saw at the beginning of this video. And this property is useful because we can characterize the continuity of functions that go out of the disjoint union space in terms of the restrictions of that function to each of the component spaces of the disjoint union. For this, we let y be some arbitrary space, and now the claim is that a function f going from the disjoint union over some family x alpha to y is continuous if and only if each of the restricted functions f restricted to x alpha, and this is a function going from x alpha to y, if all of these restrictions are continuous. Diagrammatically, we have the disjoint union here, and we have each of the x alphas along with the inclusion map iota alpha. And now we're saying that a function f going from this disjoint union space to y is continuous if and only if each of the restrictions of f to the individual component space as x alpha is continuous. If you think about it for a moment, the restriction of f to x alpha is nothing but f after iota alpha. Now we've seen that our construction makes these guys continuous. Therefore, if f is a continuous map from the disjoint union to y, then also the composite f after iota will be continuous because the iotas are continuous, and this proves one of the directions of the implication up here. Conversely, suppose that each of these restrictions here is a continuous map. Well, then we have maps going from x alpha to y, so these restricted maps for each alpha, and this means that there is going to exist a unique continuous map u going from the disjoint union to y that makes these triangles commute. In other words, u after iota alpha is equal to f restricted to x alpha, and this is nothing but f after iota alpha. Now, because we used the universal property in the category of topological spaces, so we used the universal property for the disjoint union space, this means that this map u is continuous. And now we'd like to use the uniqueness part in order to say that f is going to be equal to u. However, because we're looking at this diagram in the category of topological spaces, and f is not necessarily yet known to be continuous, we can't just say that f is going to be equal to u because they don't live in the same category. In other words, the uniqueness of u amongst maps that makes these diagrams commute, if we're thinking about it in terms of the universal property for the disjoint union topological space, this only holds amongst continuous maps and not necessarily amongst all functions. Luckily, we know that there's also a corresponding universal property for the disjoint union in terms of just sets and functions. This is what we saw at the very beginning of the video and what also motivated the universal property for the disjoint union space. So the universal property for sets and functions is exactly the same. It's saying that if we have some functions, and now we're not thinking about these as continuous maps, we're just thinking about them as functions, f restricted to x alpha into y, then there's going to exist a unique function from the disjoint union over the x alphas, which we're just thinking about as a set, to the set y. However, this map u, it's a continuous map, but it's also in particular a function that satisfies this property. So u satisfies the universal property for the disjoint union viewed as a set, but also f satisfies the universal property for the disjoint union viewed as a set, because as we've observed down here, this restriction f to x alpha is just the composite of f with iota alpha. So f makes this triangle's commute. Therefore, from the universal property of the disjoint union as a set, it follows that u is equal to f as functions. But now, because we know that u is continuous, this means that f is also continuous. Okay, and with that we've proved the other direction using the universal property for both the disjoint union as a topological space and also the universal property for the disjoint union as a set. Now, if you watched the previous video on product spaces, you'll notice that this argument is basically the same, including this issue with having to use both universal properties, except that all the arrows in the argument are reversed. As was the case there, there's also a direct proof that doesn't use the universal property. For the second proof, suppose that each of these restrictions, f restricted to x alpha, is continuous. Now we let u be some open set of y, and we want to show that its pre-image under f is open. Now, by the definition of the disjoint union topology, being open in the disjoint union topology means that the intersection of that set with each of the component spaces needs to be an open set. So we consider the intersection of the pre-image of u with some x alpha for an arbitrary index alpha. But what is this set? Well, this is the set of all points x in the disjoint union over the x alphas, such that 1 f of x lies in u, and also x lies in x alpha. But because we're thinking of x alpha as being a subset of the disjoint union over all the x alphas, this is the same thing as the set of all the x's in x alpha, such that f of x lies in u. And now finally, this set is just the pre-image of this restricted function f restricted to x alpha of the set u. Now by assumption, each of these f restricted to x alpha is continuous, so this set will be open, which shows that also this set here is open. Since this holds for an arbitrary index alpha, this means that the intersection of this pre-image under f of u intersected with each of the component spaces is open, so it itself will be open. Again, here is a warning. In this argument, I've been identifying the spaces x alpha with their isomorphic copies x alpha times the singleton alpha. For example, down here, f is technically a function from the disjoint union to y and not from x alpha to y. So here, maybe to be a bit more correct, we should write f restricted to x alpha. And then the only places where this identification that I was talking about that we're doing implicitly is happening is here and here. In any case, if this implicit identifying that's going on is causing you some confusion, you should just write out the same proof completely correctly where the identification doesn't take place, and you'll see that it still works. In summary, we've seen two proofs, one using the abstract universal properties and one using directly the definition of this characteristic property for the disjoint union space. To reemphasize, this property is useful because we can characterize the continuity of functions out of the disjoint union by simply looking at their restrictions to each of the component spaces. And conversely, given some component functions going from each of the component spaces to y that are continuous, we can assemble them into a continuous map that goes out of the disjoint union. Finally, I'll present some more useful properties of the disjoint union topology without proof. The first of these concerns the closed sets in the disjoint union topology. It says that a set C is closed in the disjoint union topology if and only if the intersection of C with each of the component spaces x alpha is closed. Thus, not only can you figure out if a set is open by intersecting it with all of the component spaces, you can do exactly the same thing for closed sets. In order to prove this, you just have to use the definition for the disjoint union topology and use complementation. The next property is that each of these injection maps, iota alpha, is a topological embedding. We haven't yet encountered this concept, so being a topological embedding just means that a map is a homeomorphism onto its image. In other words, x alpha is homeomorphic to iota alpha of x alpha. In other words, part B of this proposition is saying that we can really think of these component spaces X alpha as lying inside the disjoint union space because they are homeomorphic to their images in the disjoint union. Now, from the definition of these injections, we know that they're, well, injective because each X is mapped to the element X comma alpha. And so if we have two distinct elements, X and Y, they'll be mapped to distinct elements in the disjoint union. In particular, if we view iota alpha as being a function that goes from X alpha to its image, iota alpha of X alpha, then because iota alpha is injective, this restricted version of iota alpha will be bijective. This is simply because if you restrict the codomain to the image, the resulting function is always surjective. Therefore, the only thing we need to check in order to show that iota alpha is a homeomorphism is that a set is open in X alpha if and only if it's open in iota alpha of X alpha. Okay, well, if we have some open set U in X alpha, then if we think about U as sitting inside the disjoint union, so if we consider iota alpha of U, this set is open in the disjoint union if and only if all of its intersection with the component spaces are open. However, because U is a subset of X alpha, it has empty intersection with all other component spaces that are not X alpha. And we know that the empty set is always an open set of every one of those spaces. Therefore, the only interesting intersection will happen with X alpha itself, and, well, iota alpha of U intersected with X alpha is just the original set U, which we assume to be open. Therefore, iota alpha of U is an open set in the disjoint union space. So this shows that iota alpha maps open sets to open sets. Conversely, let's suppose we have some open set U lying in the image of iota alpha. Well, we know that iota alpha is a continuous map going from X alpha to the disjoint union, and so it's also going to be a continuous map going from X alpha to this restricted subspace iota alpha of X alpha. This is something we saw in the video on subspaces, where we saw that if we have a continuous map going between two spaces, then we can always restrict the codomain to the image of that map and still get a continuous map going from the original domain to the subspace, which is the image of that map. You can also see this more directly just by looking at the preimage of U under iota alpha, which is equal to the intersection of U with the component space X alpha. Now, if U is an open set of the subspace iota alpha of X alpha, so this is a subspace of the entire disjoint union space, then this means that U has to equal V intersected iota alpha of X alpha for V open in the disjoint union space. Okay, but this means that this set here, again with the caveat that we're making these identifications of isomorphic copies of the component spaces, this is equal to V intersect iota alpha of X alpha intersected X alpha, but we're actually identifying these two spaces here with each other. So actually we can just erase one of these guys and just have it be V intersect X alpha. Now, because V is open in the disjoint union space, we know that all intersections of V with the corresponding X alphas are open. So this means that this set here is open, which shows that this preimage up here is open. All right, so in summary, we've shown that these injections, iota alpha, not only are they injective functions from X alpha to the disjoint union, they actually define homeomorphisms onto their images viewed as subspaces of the disjoint union. In particular, because each of the X alphas is both an open set and a closed set of the disjoint union, this means that each of these iota alphas is also an open and a closed map. Finally, the last property we'll discuss concerns preservation of certain properties. It says that if we take disjoint unions of spaces, then the following properties are preserved. First, the Hausdorff property is preserved. So if each of the component spaces X alpha are Hausdorff spaces, then so is the disjoint union space. Second, if each of the X alphas is first countable, then also the disjoint union space will be first countable. And finally, if each of the X alphas in the family is second countable, and moreover this family A is a countable set, then the entire disjoint union over this countable collection of spaces will be second countable. So this last property here is a bit more complicated because we need the index set to be a countable set. And the reason for this is easy to see if you think about bases for the corresponding spaces. So being second countable means that each of the spaces will have a countable basis. And you can check that if you have a basis for each of the spaces, then you can get a basis for the disjoint union space by just taking disjoint unions of all the basis elements. Therefore, in order for this resulting basis for the disjoint union space to again be countable, one needs to have that the index set, so the family of these spaces, is themselves countable. Otherwise, you would possibly be taking uncountable disjoint unions over some basis elements, and the result would then be an uncountable set. All right, that concludes what I wanted to say about disjoint union spaces. Next time, we'll be starting to look at quotient spaces, which are topological spaces that are obtained by identifying certain portions of pre-existing spaces.